Okay, let's cover Chapter 17. Introduce Chapter 17 with Class 22, Kinetics of Rigid Bodies, Work and Energy. What we have differently, or what we had, I should say, what we began with in particles for work and energy, we're going to extend with rigid bodies. One of the key differences is going to be that we have a different type of work that can be placed onto a rigid body, which involves the moment times the angular displacement, where before we had force times a distance. Now we have moment times a displacement of the angle. We also have an additional term for the kinetic energy. We still have translational kinetic energy, 1/2 mv squared. But now, if there is a rotating body that has a mass moment of inertia that resists motion, we also have kinetic energy of its angular kinetic energy, if you would put it that way. Something else we will point out is that we have that the combination of these two right here will result in us showing again the existence of the parallel axis theorem. I'll mention that briefly down below. You could see that here we have the translational kinetic energy, and here if this drum, that the cable drum, if it has a mass moment of inertia, it too will have kinetic energy. So it'll be a combination of that translation and that rotation kinetic energy. So recall for the work, the big equation that we used for work energy was the kinetic energy before and potential energy before. So the energy before and then an external work that gets placed on it. The combination of that energy before and the external is going to equal the energy after. So we start out with something happens to it, and we end up with something at the end. It's an energy balance, if you will. That external could be positive or negative. Remember that friction is an example of a negative energy, taking energy out of the system. Okay, so we recall that work was equal to force through a distance. Important that it was dotted right here, right? So if we had some type of force vector and it went through a motion, that we were doing a dot product, which another way of thinking of it is projecting one vector onto another, resulting in a scalar, because another name for the dot product is the scalar product. And so it's not force times a distance, it's force through a distance. It's only the distance that's in line with the force, or vice versa, the force that's in line with the distance. So similarly, what we have for when we have rigid bodies, we can have rotation. So we want the integral, the moment as a vector right here, and it's going to be times d theta, and that's going to go from theta 1 to theta 2. Now, the most common case for us is when we're going to have a constant moment. That's probably what we'll see most often. And if that's true, then this is just going to be equal to the moment delta theta. And you want to think about the relationship between these two right here. We could take for a circle. Let's say that we are moving in a circular pattern right here, right? And we'll change colors. And there's a force that's being applied right there at the edge tangent, and we have a distance r to the center. right? If we take that force and we look at it as it passes through various points right here, we could say that the work between, let's say this is 1 and this is 2, we could say that that work was that force times that distance, which turns out to be an arc, right? So that's going to be that arc length starting at 1 and going to 2 is going to be r delta theta, right? That's a constant force that's moving along this arc. Well, we also will know that that force times that distance is also a moment, right? So it ends up being really the same thing on one level. Or it can be demonstrated that these are actually, we're looking at the same thing. The kinetic energy of a rigid body in plane motion here, we had, for translation, we had 1/2 mv squared, but now we're going to say 1/2 mv at the center of mass squared. So this is the translation part of the combination. Remember, all rigid bodies can be broken down into a combination of translation and rotation. So now, if something can rotate, as we previously mentioned, we have this rotational kinetic energy of 1/2 I omega squared. For potential energy, we still have gravitational potential energy for the translational side, but there is no really rotational equivalent of this. But for linear spring, we had 1/2 kx squared, or I prefer to say 1/2 del k del squared, because I wanted to emphasize that we're not talking about a translation here. We're talking about an amount of spring stretch. So whatever the spring stretch is at a particular state, that's the del. That's the amount that it is changed from its original length. It could be a stretch or it could be a crush, right? We could be in tension or compression. The spring doesn't matter. It still stores up potential energy. There is an equivalent here that we could use. We probably don't run across it very often, but we have 1/2 k, and I'll stick a theta in the subscript and then say a theta squared. And maybe I should say call it a delta theta squared. I didn't really have an equivalent to the del going on right here, but it is a change in angular position from its unstretched or uncompressed location. And examples of this kind of spring might be for a watch or a clock or a wind-up toy, where you're coiling this thing up and you're storing the energy, and the amount of rotations in radians that you turn is going to determine the amount of that you've put in, the energy you put in. You could also have another type of coil spring like here that's going to be a torsional spring. One example might be in the old kind of clothespin, or in a rat trap, where you set the rat trap and you store energy in the rat trap, and then when the rat comes and eats the cheese, it lets it go and all that energy comes out of it. So you could think of these potential energies as in springs as energy storage devices. And we apply the big picture here. We are able to sometimes, in some parts and some pieces, use a strategy to because we have the choice of applying energy methods either to individual objects or to entire systems. That's a really good attribute of this energy method. And sometimes it's we could do it multiple times, or solve a problem multiple times, for sometimes with the individual objects or the system, and that allows us sometimes to ignore internal forces or to obtain internal forces, and that can come out in some cases. All right, so here's caveats to remember when you're working on work and energy. Let me blow this up a little bit bigger. I'll discard all this other stuff that I had right here. And I'll put this over to the side. This was formatted to fit onto a whiteboard screen. Okay, so once again, some of these are reminders, and that we have positive and negative energy, right? The positive is when the work is input into the system. Energy is when it's removed, for instance, with friction. The direction of the force and displacement is also another way to think of this, as if they are in agreement. Right, if the force is going this way and it goes from here to here, right, and so the delta x is in line and traveling in agreement, right. And let me get rid of that arrow. Let's say he's moving that away, right there. Yes, that is positive. But if the force is going this way, and maybe I should draw it over here. Force is going this way, but we've moved that way, that's going to be negative work, right? That is work removed from the system. And the same thing is true if the moment is going this way and the delta theta has gone the same way, right? That they agree. But if the moment, let's say there's something resisting the motion, and it has moved this direction right here, this is going to be negative, whereas this is positive. Same thing up here. That's positive, and that's negative. When you have two parts, the translational and the rotational, you can connect them together by saying, in this case right here, that V is equal to R omega. And therefore, when you have the 1/2 mv squared right here, plus 1/2 I about the center of mass, omega squared, right? You can have 1/2 m R omega squared plus 1/2 I about the center omega squared. You can take the omega squared out and the 1/2, and what you're left with is I bar plus m r squared, which is the parallel axis there, right? So you have an equivalent I-O about the center that you can use, because you've moved the moment of inertia from being about the center of mass to this point. Make sure you don't double dip. You can only need to use this when you have the situation where you're moving about a fixed point. An interesting thing about the wheel that moves without slipping is that you can ignore the friction in this case, because the power is equal to force times velocity, right? And work can just be considered as the integration of power versus time, right? So we are left with this right here. If the velocity at the point of contact in the no-slip condition is 0, the power is 0, therefore the integration and the work or the energy loss due to friction is going to be 0. That's an important comment. Now, we know that the conservation of energy occurs when there is no external work, either added or subtracted from the system. So the energy before is equal to the energy after. And do I have anything more? Yes, I do. We might ask ourselves, when should we use work energy instead of Newton's second law? And as a general principle here, Newton's second law is advantageous when you have accelerations. And in our case, whether it's going to be a translational acceleration or it's going to be angular acceleration. So work energy is more suited or is most helpful to us when we have we have a velocity, angular velocity, or a delta x, right? So we've moved a certain distance. And we're covering it in next class, but impulse and momentum similarly is advantageous when there's a velocity or an angular velocity, but now when we're dealing with a delta t. Also, when there's impact involved, and we want to contain that impact inside a system, there can still be energy losses in impulse and momentum, but not angular, but angular impulse and momentum can be conserved, and we'll see that in the next class. It's a separate thing. But there are some problems where you could use all three methods. And I believe this is the last one. We have something, as I mentioned before, that power was force times velocity, but even more interesting for us when it comes to angular things, we have power is also equal to moment times angular velocity, which in practical terms we'll often see in machines, especially cars and other things. Power is torque times RPM. Now, there is some conversion factors that are necessary to be able to get things into the normal units that we are used to, but you could just think of that. Torque times the moment times the angular velocity is equal to power. Therefore, torque times RPM is equal to power, and we can use that to to understand the trade-off between torque and RPM, including if your car needs to go up a hill, you want to downshift the engine, because your engine only has so much power, but it can divvy up that power towards the torque side of it, so you can get more torque, so you can have more pulling power or climbing power up a hill, or you're pulling something behind you, a trailer or whatever. So you could use that power to its advantage by having a low RPM, which will allow you to have a large torque. And the same thing's true if you're like on a bicyclist, right? It's like you only have so much power they're able to exert. But now, if you change the gears and you change the RPM of the output of the wheel, you will be running your pedals much faster, but you'll be able to get much more torque, and so you'll be able to overcome a much more steeper grade. Right, so that you're able to apply torque into to the output wheel. So just one note on units: 550 foot-pounds per second per horsepower is a very common unit that you'll need, because we use horsepower in U.S. units. And also note that torque times RPM requires a little bit of adjustment to turn RPM, revolutions per second, into radians per second. Multiply that by Newton meters, and we get Newton meter per second. It's also called a joule per second, aka a watt. So that's what today's topic is, and we can discard this, and we can add in a little Van Halen. We have a guitar pick somewhere. And we have the replica of the Shark guitar from Women and Children First, the third Van Halen album, where he has destroyed it by cutting the guitar apart. And if we were to turn this up some, about the pick scrape. It's pretty simple, I guess, right? It was not a good picture. Great. Didn't do a very good artificial harmonic there. Can't remember that one. This guitar. That's all, folks.